giving us the closing things. Thank you so much.
Okay, can you hear me? So I'm told that I'm the only thing that stands between you and happy hour. This is a very, very bad position to be in. I was asking Flanders whether maybe we could combine the two events, like have happy hour right here. That would be very cool. Thank you to Jonathan and Flanders and the rest of the organizers for giving me more time to tell you about what we have learned. It's going to build on what I explained this morning, okay? I've organized my talk today into two parts. One is a set of broad thoughts about standardization, because obviously this is a big deal to have standards at the edge that make it possible for the kind of ecosystem growth that is necessary for scaling. So that's one. The second part of the talk is about what we have learned about using OpenStack for the kind of edge computing applications that I described this morning, okay? So this includes extensions to OpenStack that we have made and released open source. They're available for you to build on, and so you may find them of interest. So let me start with a picture that you already know very well, which is the internet ecosystem, right? So this is found in every textbook on networking. The part about this that you may not have known are these two numbers. These are the latest numbers that I could find for the top and bottom half of the value in the internet ecosystem. So the top part are companies like Zappos, Amazon as the seller of items, and so on. The bottom half, and Google, of course, and the bottom half are the companies, the market cap of the companies that make the technology for the internet, like Cisco, Juniper, Intel, and so on. So those numbers are astounding. In 2013, there was $5 trillion T value in these two. So that is the internet ecosystem's value. The point of this slide is to ask the question, what holds it together? It's IP, TCP, UDP, DNS, ICMP, right? HTTP. I mean, I'm on to my second hand, but I'm not sure I will need to use the rest of the fingers. Maybe SSL, TLS, right? I definitely won't have to use all my toes. So the question is, how does something worth $5 trillion arise from something that can be specified in less than my number of fingers and toes, right? The answer is this reason, that as long as authentication, authorization, and billing, right, as long as the security and billing aspects are met, any end-to-end service anywhere in the world can use any network. That universality is extraordinarily powerful. The choice of the network may depend on pricing. You might have Wi-Fi, you might have pricing network, pay by the byte costs for your cellular network. Obviously, you choose the Wi-Fi, even if its performance, heavily loaded, is worse than the cost-paying alternative. There may also be performance criteria, latency, bandwidth, etc. The one thing that it does not do is depend on software compatibility. IP is IP everywhere in the world. So we arrived at this state of affairs over an evolutionary period from the late 1960s through the 70s, through the 80s, to the early 90s when the World Wide Web was invented. Okay? And even by the time of the World Wide Web, enough internet infrastructure had been deployed that when this killer app emerged, it was able to take off. Okay? So I would like to propose to you the equivalent principle for edge computing. If we can arrange over the next few years for the evolution of edge computing to follow what's said here, then I suggest that an ecosystem as valuable as the internet can be created. Maybe not the exact same numbers, but certainly very large value can be created. And so the principle is, as long as authentication, billing, and authorization criteria are met, any end-to-end service that is running on any device should be able to use any cloudlet in the world. The choice of which one to use may depend on pricing, current pricing, if it's use pay by the hour kind of thing rather than ownership of the cloudlet. And it will certainly depend on things such as latency, bandwidth, presence of storage, presence of special hardware accelerators that might be needed by your application. These are all perfectly fine reasons for choosing one cloudlet over another. But what should not be at stake is whether your backend can in fact use that cloudlet at all in terms of software compatibility. Okay? So how do we get there from here? One of the lessons from the early internet, which is very powerful, is that standards are rarely successful in creating anything like the internet ecosystem if they are imposed top-down. The standards that co-evolve with valuable applications turn out to be incredibly valuable standards. And those have lasting power, but you have to discover them and co-evolve them with value-delivering applications. For example, the kind of things that I showed you this morning, and also many other applications that I presume are waiting to be created. Remember, in 1969, nobody thought of email. There was no concept of FTP. It was the presence of the network, the ability that it provided. It took creative effort to create the concept of email. Once created, it was obvious. And of course, today we take it for granted. But those applications made the network more valuable. So this is essentially the critical insight from the internet. One of the best discussions of the early evolution of the internet and why it succeeded was given by David Clark, who's a professor at MIT. And that quote is from a paper of his: "We reject kings, presidents, and voting. We believe in rough consensus and running code. Rather than agonizing over the perfect API, it's much better to get one that is good enough for now, with the willingness and recognition to change it during a certain evolutionary period. If one can have a window of time where standards can be malleable rather than rigid, that gives you the window in which to create these kinds of standards. Remember, the only thing worse than not having a standard is a bad standard. So some of you may remember a thing called WAP, Wireless Access Protocol. That is a perfect example of a top-down standard which should be used as Exhibit A to substantiate the point here. Another point I want to make is that unless new end-user value is delivered, edge computing is merely going to shuffle the value chain. Ultimately, it is end-user value. There's going to be billions of people on the planet who derive value from edge computing, who are going to be the source of the new value that is created in the ecosystem similar to the one for the internet. And so encouraging applications, new applications, not taking existing ones and saying you can run it a little better on the internet. There is ample evidence that in the early history of personal computing, it was the Lotus 123 spreadsheet that drove the sales of IBM PCs. Mom and pop stores were willing to plunk down $10,000 for an IBM PC XT, which is what you needed to run Lotus 123. Now think about it. The total revenue, annual revenue of many of these small mom and pop stores was less than 100K. 10% of their annual value was worth to them. Now, what did it do for them? They saw immediate value in terms of improving their own business. The question is, why did it have to wait for the IBM PC for the spreadsheet to emerge? You could have created it in a time-sharing system. The answer is it was the low latency. When you change one number on a spreadsheet, the instantaneous changing, it's almost like a live whiteboard that worked for people. So I would like you to think along those terms in thinking about the future of edge computing, that it's going to be these transformative applications. And so here we have a chicken or egg problem. All the guys who are startup company people, entrepreneurs, wonder, can I build something that depends on low latency, that depends on all the attractive characteristics of edge computing, if there is no edge computing deployment out there? The companies who are making those investments ask the question, where are the applications? And so you have a deadlock which needs to be broken, and until that happens, it is going to be not going to take off in the way that it has the potential to do. And I'll say in a moment what we are trying to do to help. I also want to share with you some thoughts I learned from David Clark about the best time to create standards. Okay, so he actually drew this picture on the whiteboard for me roughly around 1991. Okay, and he's forgotten that he actually did this. When I showed it to him, he said, "My God, did I tell you that?" And indeed, he is the person who gave this to me. So on the x-axis is time, and on the y-axis is some rough measure of activity level. Okay, so there's some new idea, some bunch of academics, maybe in universities, but sometimes research labs, experiment with the idea. It's cool, seems to have a lot of buzz. The papers published, prototypes built, PhDs generated, etc. And then people move on. By this time, this idea is old hat. At some point, industry starts seeing the value of this, makes investments, derives value from it, and after some point, if your product does not incorporate whatever this innovation was, it's no longer in the running. So it becomes a standard part of the product offerings. So, the exact details, notice there are no numbers. So, the two curves could be very close together, they may be far apart. All of these happen in the real world. But the interesting question is, when is the right time to define a standard? Okay? Because it's very relevant to edge computing. If you tried to do a standard here, and many people would love to do this because it gives you first mover advantage. Okay? There's a very good chance that it will be a bad standard. It's too early in the technology. You have not fully understood its implications and its strengths and weaknesses. What you're proposing to freeze is likely to be bad for the long-term growth. If you try to do it here, industry has already made a lot of investment. Nobody's going to go back and undo that investment just to be compatible. So there is this little window. When enough experience has been gained, perhaps in experimental, perhaps in proof of concepts, perhaps in pilot deployments, but not too much industry investment has been made. There's a sliver of time during which there's enough flexibility to propose and define a standard that builds on what was learned here. And so the perfect example of this is the Ethernet standard. So Xerox, as part of the Alto project in the 1970s, developed the 3 megabit Ethernet. And then at the end of that time frame, in the early 1980s, Xerox solicited Intel's and digital equipment companies, a company that no longer exists, their partnership based on what they had learned to create the 10 megabit Ethernet standard. And as you all know, with minor improvements and changes, it has gotten us a long way. Today we have 10 gigabit Ethernet standards that are very successful. So the question in all your minds is obviously, where are we on this graph with respect to edge computing? So my judgment is that we're roughly here. There are people like my group and others who have gained some experience with edge computing, and there are companies like GE which have made significant deployments of edge computing internally. So there is learning, but there's not yet huge infrastructure deployments. So my estimation is that this window will start somewhere around early next year, 2018, probably last a year or two. And so we have the opportunity in that time window to lay the foundations for a very good ecosystem that could emerge and have long legs that last many decades. Or there could be fragmentation, and how it all plays out depends on you. Okay? To help, what I'm doing, along with a number of companies that are listed at the bottom here, is creating in Pittsburgh at Carnegie Mellon University, but also the region surrounding us, a living edge lab for edge computing, so that people who want to experiment with pilot applications and gain real-world experience, we provide the Cloudlet in our lab, so you don't have to deploy it. Some of these companies are paying for the wireless network access. The 3.5 gigahertz Altiostar network is the first one. Commercial T-Mobile network is another. We would love to include additional radio networks that people are interested in deploying and exploring. And also, equally and more importantly, example applications, pilot applications. This is not for commercial revenue generation, but to gain experience with these applications and possibly pilot deployments. So Rolf Schuster, where's Rolf? Are you here in the room? There he is. He is the person who helps me shepherd all these companies, so talk to him if you'd like to be involved in this. We have a loose collaboration called the Open Edge Computing Initiative that Rolf is leading. And in fact, we are proposing by the end of this year to have 3 areas: the Carnegie Mellon campus, a outdoor test bed in a region close to the university, and another test bed in an upscale shopping district where examples such as augmented reality and other applications can be tested in real business environments. Okay? So looking ahead to the future, here's some thoughts. And I've tried to paraphrase these in pithy short terms. There are going to be many kinds of cloudlets. There isn't going to be one. There are going to be telco cloudlets, which are very well managed. They're going to be maintained, run. The kind of problems that were talked about this morning and this afternoon apply there. There are also going to be much smaller cloudlets. An Ubuntu Orange box with suitable modifications would be an example of a cloudlet. In a rural area where the telco coverage says, there's not enough demand for edge computing, I'm not going to put cloudlets out here, you may have to buy your own from Dell or Lenovo or somebody, assuming they make these, and put that in your basement. So automobile cloudlets, aircraft cloudlets, Wi-Fi based home cloudlets, telco cloudlets, there are going to be many. But from the viewpoint of an application developer, they should all look the same. If he develops an application like one of those I showed this morning, maybe an assistance application for an elder person, it should be a second order detail, whether I have to buy my own cloudlet or whether I rent time from a Verizon Cloudlet deployment in my neighborhood. And that should be, it should not be a question of whether my application will run on it. It should only be a price question or coverage question. So this is exactly the point that I'm making here. One application, many cloudlets. The value chain begins with the end user. I've already made this point, and I can only emphasize it. This last point is a little subtle. The edge is real, the cloud is abstract. For the last decade or more, we have viewed the cloud as a source of all wisdom. Google Maps comes to you from the cloud. Facebook comes to you from the cloud. Everything we use every day comes to us from the cloud. But the reality is that the edge knows better than the cloud. The bridge that is so beautifully marked on your Google Maps may be covered with water if you live in Houston right now. Okay? So it is the edge that has reality. So for example, imagine a system in which automobiles with video cameras automatically detect obstacles, potholes, rocks, lanes that are closed, and just like Waze, but automatically, without human intervention, report them. And then it's disseminated back to your navigation system. You are now benefiting from live information processed at the edge, crowdsourced, and overlaid on top of cloud-generated information. Eventually, some of this may get back into Google Maps. But some of these things may be too transient. The rock in the right lane that matters to people right now, should it really make its way into Google Maps? Depends how long it's going to be there. Hopefully it'll be moved out, or the dead carcass of some animal that's roadkill. It's another example. So as you think about edge computing and edge computing deployments and what kind of infrastructure you need, I suggest that these are 4 points to keep in mind in thinking about them. I'd like to now switch to the second part of my talk and tell you what we have learned and what we have done with OpenStack. So some years ago, when we began working with edge computing, we asked the question, what should we build on? We could build it completely from scratch, a new platform for edge computing, or we could take something that already exists, modify it minimally, and use it. And we chose the latter approach. OpenStack has many shortcomings. We could spend the entire happy hour discussing them. Okay? And it'll be a mutual catharsis session. But that's not the point, right? For purposes of prototyping, for getting us there, the concepts of multi-tenancy, the ability to manage virtual machine images, the ability to have metering, which is important in business models, all of those things come with it. And so trusting that the negatives of OpenStack can be cured over time, we said, let's start with it and go with it. So we worked with the kilo version of OpenStack. And there's a bunch of people here from a company called InWinStack, Joseph and Thor. Where are you? There they are. They're from Taiwan. And they have taken our work and ported it to the Newton and Okata ports. Is the Okata done? Well, it's still in progress. It's done. OK, fantastic. So in asking what we should do to OpenStack for edge computing, we were very conscious that we wanted to be minimalistic. So there's a famous quote, which I've listed there, that says, perfection is reached not when there's nothing more to add, but when there's nothing more to take away. So we asked the question, what is the bare minimum that you have to add to OpenStack for edge computing? And we came up with 3. And then in actually trying to build the Living Edge lab this year, we discovered we needed one more. And that's the 4th one listed there, Cloudlet Launcher and Gateway. So the 3 things we thought of and we implemented were discovering the cloudlet. So if you're using the cloud, there's only one cloud, the cloud, right? Maybe there's a question of, do you want Amazon West or East or Asia? But usually it's not a big deal. You have basically one question, which is the cloud. But cloudlets, there could be many of them. So which is the optimal one? In terms of latency, in terms of bandwidth, in terms of having the lightest load, in terms of being close to where I might be going shortly, in terms of having the right hardware accelerators for this unique application, etc. The second functionality relates to the conversation in the previous session about thin control plane, etc. If you have a data center, things within it tend to be well managed. But if you have many different kinds of cloudlets strewn all over the place, some of them may be beautifully managed professionally, others are not going to be so well managed. Somehow, in order to have true universal access, you need to be sure that your back-end image, assuming it's a virtual machine or a container, somehow, no matter where in the world you go, you have to be able to rapidly provision it, even if it hasn't been correctly pre-provisioned. So rapid cloudlet provisioning, using a technique that we call dynamic VM synthesis, is something that we've implemented. It's part of the open source extensions, and I'll show you some numbers that tell you how good it can be. Basically, you can provision and launch a new VM instance in the order of 10 seconds, even for a gigabyte-sized VM. Okay? The last capability that we thought of is, unlike the cloud, which has got excellent connectivity internally and is in a safe place, a data center is like a fortress, right? I'm sure if there was a data center in Houston, it was not submerged by the floods. Presumably they thought of it and built it in a way that would even withstand that. That's not going to be true for the kind of cloudlets that are deployed in someone's basement, right? It is going to get flooded. So the ability to move VMs, possibly live service VMs, across cloudlets over the wide area internet is a very powerful capability. And so VM handoff, and I don't mean here, when I use the word handoff, people immediately think of wireless handoff, access point handoff. Those happen very frequently, and they're very fast. VM handoff only has to happen when conditions change enough to merit the movement. So if it takes seconds or tens of seconds, that's okay. And you don't need it to work at millisecond granularity. And then the last one, Cloudlet Launcher and Gateway, arises because there are limited numbers of IP addresses. And I'll explain more about that when I get to that part of the talk. Okay, so let me very quickly, I'm only going to summarize these points. And each of these capabilities is described in a paper, technical paper that is available off my website. You can get all the details. So the basic idea is we have loosely managed cloudlets where the management aspect has two parts. One is security, physical integrity of the machine. We have not done anything special there. We count on hardware vendors to create the necessary tamper-evident, tamper-resistant, tamper-sensitive enclosures so that even if somebody holds a gun to the barista's head and says, I'm going to tamper with your cloudlet in the Starbucks, you'll at least know that it has been tampered with. You may not be able to prevent the guy from doing something bad, but you'll be able to detect, right? So the security of the cloudlet is a separate problem that we have done nothing about. The second problem is no matter which cloudlet you use, if it doesn't already have exactly the bits you need, you can instantiate them very quickly, okay? So here's a basic idea. Imagine a traveler, say it's you. You have a business trip to some part of the world where English is not spoken widely. Maybe it's, say, some part of Central Asia, Tajikistan, Kazakhstan. You get off at the airport, you have a translator, but it depends on a backend that runs on a cloudlet for low latency interactivity. but they don't have your customized image. It's present in the cloud, in all the well-provisioned telco cloudlets that you're used to normally using, but here, when you need it most, it's not there. Fortunately, the VM image is on your mobile device, okay? And you have high bandwidth connectivity to the cloudlet. Imagine just in time, in the order of 10 seconds for an 8 gigabyte VM, you are able to instantiate and launch it. How can you do it? Here's how it works. Basically, recognize that most VM images are not made from scratch. You start with an existing, widely used image, and then install the unique libraries and applications you need into it, and you derive from that the application. Now, it turns out, and we have lots of measurements that have shown this, that delta, in terms of number of changed bits, is quite small. It's between 1 and 10% of the size of the original VM. So what you can do is to make sure that all cloudlets in the world are pre-provisioned with a small set of widely used base VMs. Hopefully, and you can publish the list, right? This is a well-known public list of base VMs. If your delta, which we call an overlay, you can in fact make it for many of these, so that the chances that you will find a compatible base VM anywhere in the world is actually quite high. So what you can now do is dynamically transmit just the overlay, which is only now a few hundred megabytes rather than 8 gigabytes, and basically generate within a few seconds a bit exact VM image. In fact, it is more likely to be perfectly bit exact than if you try to do the install of the original sequence by hand. Okay? Now, so here's how it works. You associate with a cloudlet. This is the first step. And then the mobile device transmits the private overlay. The cloudlet synthesizes the base and the overlay. And now it has the exact VM images, it launches it. And once it's launched, the application, like the ones I showed you this morning from your wearable device or this natural language translator, use this cloudlet. Now, in some cases, you do machine learning as you use the system. So the final state after you use the cloudlet is actually important because it represents important learned information. So the cloudlet can generate another overlay, which we call the residue, and send it back to the mobile device so that you're carrying with you the delta relative to the base VM of the current state of your computation. And you're carrying it with you physically. And of course, you can also transmit it back to wherever your cloud or your provisioning entity back home, if in addition you want to protect yourself against losing your mobile device. Okay? So when we first did this, by the way, there are multiple variants of this. You can, if the bandwidth to the cloud is good, you can get the bits directly from the cloud, but under the control of the mobile device. It's also possible to have a complete cloud orchestrated version of this. So all of these are possible. We have shown how to do it. It all works. The interesting question is how fast did it? So we did this for 5 applications. This is object recognition, so computer vision, face recognition, speech recognition, augmented reality, and this happens to be a computer graphics application. Okay? Notice that some of them are Windows 7, some of them are Linux, Ubuntu. This thing doesn't care. It's working on the bits of a VM image. So the technique is OS agnostic. Okay? The number that I want you to look at is this at the end. This is how long the unoptimized flavor of doing this takes, between a minute and 2 minutes. Not bad, but not great. I mean, this is not user experience of waiting a minute before you can talk to somebody or recognize somebody is not great. So what can you do? So it turns out you can do a lot. It turns out that a lot of the bits are already present at the destination in the VM image, so you can use deduplication. The number of clever techniques that infer that there is commonality between the memory state of the virtual machine and the disk image. Even though it's not explicit, you can detect it. So this is what I mean by bridging the semantic gaps. The other thing you can do, so this reduces the total number of bits you have to send. The other thing you can do is launch the VM instance before the image is really there, and effectively demand page the parts of the VM image from the mobile device, or accelerate the synthesis if you happen to touch a part of it that is needed. Okay, so that's what is early start, and pipelining is a technique to get all this working efficiently. So the net effect is huge. So these were the original numbers that I showed you in the graph, right? Somewhere between tens of seconds to a minute to 2 minutes. These are all in seconds. If you downloaded ahead of time all of the right libraries and bits needed for installation, and you only did the install into a base VM image, the green is how long it would take. Okay, and it might not work. You've all had the bad experience of following steps in an instruction perfectly, but it breaks, right? So scripts that have to be executed break. The red gives you the bit exact VM image with no likelihood of failure, and it's faster. It's under 10 seconds to do it, right? So that is rapid provisioning. The notion that you can instantiate a huge VM very quickly any way you want is very powerful when you're thinking about control plane, provisioning, management, etc., because it's a very powerful management tool. Let me now tell you about adaptive VM handoff, which is the second capability. Imagine our patient that we talked about this morning visiting his neighbor. He has a Cloudlet in his home, which is running the back end. He visits the neighbor. Of course, he's using the neighbor's Wi-Fi, but the VM instance is still running in his home Cloudlet. Because his neighbor uses a different ISP, the total end-to-end network delay is quite significant. The latency is beyond what is optimal for the AR application that he's using. So this is the kind of situation in which being able to migrate the VM from his home Cloudlet temporarily to his neighbor's Cloudlet would be useful. Similarly, if I get into my car and drive, I would like my execution to happen in the automobile Cloudlet in the trunk or near the engine. So when I'm getting into the car and the time it takes me to leave home, I would like the VM instance to be running on the automobile Cloudlet. When I get off at the beach and walk far, I would like the VM to be running on the telco Cloudlet because that's the only coverage I have out there. So this kind of VM handoff is something that you do in data centers today and is referred to as live migration. Okay, it's well-known, standard practice. It was described about 12 years ago in 2005, and the technique is used VMware, both OpenStack as well as many other systems, cloud computing systems use it. The problem is it only works well at gigabit per second or better bandwidth. So typically inside a data center, I have gigabit, 10 gigabit, 40 gigabits if I'm really fortunate. But between cloudlets, I may have 10 megabits per second, 3 orders of magnitude smaller than inside a data center. So can we make it work? And the short answer, using techniques such as the one that I just mentioned, is possible. So in the interest of time, let me skip to some numbers. So this is object recognition, like the augmented reality application I showed you this morning. Our implementation is able to move the whole virtual machine while it is being used, just like in a data center, from one cloudlet to another over a 10 megabit per second network, okay? This is wide area internet, in the order of a minute. And there's a brief period, just at the very end, when the system, the last step of the handoff requires the system to be quiet. The duration of that is just over 5 seconds, okay? So you suffer bad performance for this long, and at the very end, it's unresponsive for that long. So, you know, if you're visiting your neighbor for half an hour, the first 5 minutes might be bad performance, but the remaining 25 minutes give you excellent performance. KVM live migration, which is what the standard OpenStack uses, on the same bandwidth, would take over 12 minutes. It's optimized for downtime. And so that part of it is good, but it comes at the price of the user suffering much longer. Now, this doesn't seem so bad. It's only 1 order of magnitude worse. Here's augmented reality with the Windows guest operating system. Here, VM handoff, our implementation on 10 megabits per second, completes the whole thing in 4 minutes. KVM live migration takes close to an hour. Okay? Remember what's going on. This is live migration. So you transfer part of the bits, but because the code is still executing, some of the memory state changes. And then you have to copy those bits over. And while you're doing that, more bits change. Now, if you're fortunate, the rate at which you're copying the bits over is faster than the rate at which bits are being dirtied. And so there's a point at the end where you converge. But if you're unlucky, for example, Windows may have been running Windows Update for all I know in the background, okay? It has a tendency to do that. If you're unlucky, then in fact you get inordinately long periods. So the implementation pays attention to the fact that our goal in wide area cloudlet to cloudlet VM handoff is very different from the goals within a data center of live migration, even though superficially the concepts are very similar. Okay, so one of the interesting questions is, would life be much, much faster with Docker? The answer, surprisingly, is not necessarily true. So with Docker, you can't actually do live migration, but you can suspend, transfer the bits, and restore. Right? So it's checkpoint, I think it's called checkpoint restart, CRUID. So for the two applications, now first of all, Docker only works, at least the implementation we used only works on Linux. So on this application, VM handoff takes up twice as long as Docker. Right? So that's not bad, given that Docker containers are so much lighter weight than VMs. For VM handoff, that's not a bad price. Surprisingly, for this application, the VM handoff takes half the amount of time as Docker. It's faster than Docker checkpoint restart. It turns out that all those optimizations for deduplication end up transferring fewer bits, only 61 megabytes instead of 98 megabytes. Okay? So I'm going to skip some of the details of the implementation and get to the last functionality, which is Cloudlet Launcher and Gateway. So I told you we're building the Living Edge lab. Well, one of the first things that we discovered was we didn't have enough IP addresses. So Crown Castle, which is one of our partners, gave us a block of 6, very generous. Well, that's wonderful, but we want to support hundreds of thousands of users with their mobile devices using services on the cloudlets. How am I going to do it with 6 IP addresses? So the short answer is to do the following. Let me get to the answer. The Cloudlet service appears as a private IP network on the device. There's plenty of private IP. So when you instantiate a service on the Cloudlet, and it could either be a web server, which is already running, or in some applications, it may be a brand new VM instance that is just yours. you effectively see it as a private IP address. And interestingly, in the presence of VM handoff, that private IP address can be preserved. The way we do it is by combining it with OpenVPN. We establish an OpenVPN tunnel between the mobile device, we've implemented this for Android, for the mobile device, to the OpenStack-based Cloudlet, and the VM endpoint to VM endpoint, VM instance endpoint to mobile device is a tunnel that is supported by OpenVPN. So all of this happens. There are two components. One is in Google Play Store. That's the Cloudlet launcher part that you can just download and install. And then in your Cloudlet, we have a Cloudlet gateway, which basically uses, I'm trying to recall the right component of OpenStack. I think it's called Heat. Is that one of the components in OpenStack? Right. Uses the same. So any description, I think there's a description which describes for Docker containers how you should connect VMs together, etc. It's completely upward compatible with that description. So any ensemble of VMs and containers that you need to launch on behalf of a mobile application gets launched, and you get a tunnel that talks to them. Okay. In the interest of time, since I have only 1 minute, I'm going to skip Cloudlet Discovery. It's a long story, and the short answer is less is more. We spent years trying to be very clever and came to the conclusion that the best way to implement this is to have only a skeletal structure for Cloudlet Discovery and allow third parties to install the cleverness, proprietary algorithms for optimal Cloudlet Discovery, because in many cases, optimality is not technical. It is not always the lowest latency, but it might be that I have a business relationship with this company, and I preferentially prefer to use that Cloudlet rather than something that is technically better. There's no way to have a compact piece of code that can capture these business relationships. So the approach we have taken is flip it on its head and say there's a skeletal structure. It reaches out to potentially proprietary algorithms that return to you the IP address of the Cloudlet you should use. Now, we provide example, which you can use if it's useful, but the assumption is you can install anything you want. And that piece of code can embody your business relationships and other criteria, and also you, the developer of the application, know your application best. So it is possible for you to prioritize different properties such as jitter, latency, bandwidth, etc. Okay? I'm already over time, so I am going to skip this. Okay, maybe I won't. Can I take 1 more minute to give you this information? Are you guys okay? All right. So I showed you many examples this morning. So when you run those kinds of applications at the edge, where does the time go? So ping pong is that application. Okay? So the way to read this is when you run this application on a Cloudlet over Wi-Fi, the total end-to-end service time, request response time, is 92 milliseconds. Out of those 92 milliseconds, the red part is on-device encoding the video that is captured. Then the green part is transmitting it from the mobile device to the Cloudlet. The yellow is the time spent processing on the Cloudlet. That's the back end. And then the blue part is the time it takes for the reply to come back to the mobile device. Okay, so that's the story across the board here. So for the fastest applications, which happens to be pool, 70 milliseconds total time, about half of it is spent on the mobile device just getting the image from the camera, encoding it, and shipping it. Not even the network transmission time, but just getting it to the network buffers. Okay? As you see, when you go to the cloud, in this case Amazon West, both the upstream and the downstream can be significant. Okay, and you look across here, in all cases, going to the cloud increases the green and the blue. But the yellow, the processing remains roughly the same. The second point I want you to note is how horribly large the yellow part is with the more sophisticated applications. So things like that IKEA lamp construction, the computer vision code to recognize those complicated parts in an IKEA kit are considerably harder to write than the code to recognize a ping pong ball. Okay? In fact, it's based on deep neural networks. And it turns out that even with multiple cores, you give it as many cores as you want, and this one is on Amazon, it still dominates. So one of the lessons we have learned is cloudlets, edge computing, for the kinds of applications that are going to be emerging, are going to be severely in need of hardware accelerators, GPUs, possibly ASICs, possibly FPGAs. There's a huge amount of work going on at many sites on speeding up using hardware accelerators for machine learning, deep neural networks, and these kinds of applications. And much more than in the cloud, for the class of applications that are going to run at the edge, there's both an opportunity and a challenge. For hardware vendors, if you're Dell or Lenovo or somebody, this is an opportunity. Okay? If you are a telco, this is a challenge because management of heterogeneous cloudlets is much more painful than uniform boxes which can be managed similarly. But that is the challenge that faces us. Okay, so I just want to repeat the points I made earlier. I'm already 2 minutes over time. I'll stop here and take any questions people have.
Yeah, I think we can afford one brilliant quick question, though let's quickly give a round of applause to what I'm officially calling Dr. Edge.
Thank you.
We can take a quick question. We got one there, so let's take that real quick.
So thanks for the great presentation. Just a quick question. What was the reason for Docker container has a worse, or I guess bad performance compared to VM in one of your table?
I'm sorry, please repeat what you're saying because I'm not hearing
performance for containers, Docker containers, was almost twice as much as the VM performance. What was the reason for that?
Our experience has been that VMs do not significantly increase end-to-end latency in our applications compared to containers. What they do is have a much larger footprint on the cloudlet. So the scalability in terms of how many users you can run on a cloudlet is certainly hurt if you have one VM per user. But the performance per user does not significantly change. The additional path length caused by the VM, we have not seen it to be sufficient to hurt these applications. Is that the question you're asking?
Let's hold it here because we're actually just running out of time. And more importantly, I think, are you coming to the drinks this evening?
Briefly.
Briefly. Okay, so let's ask some questions there. Just one fantastic, again, I'm codenaming you Dr. Edge because I've just loved your So everyone, please, massive applause for Professor
Thank you. That's a new name. Nobody has called me that before.
I love it. Professor Edge. We're sticking with it.
Thank you.
Okay, so next up, we are, of course, headed to drinks. I believe we will have a walking party just outside here. Heidi and Nicole. Nicole and Heidi, could you quickly raise your hands just so everybody can see you? Please head with them. They will escort you to where we're going to have some great drinks. Thanks again to everyone, and we'll see you tomorrow.
It's like the first time when we opened